Hi everyone, welcome back to CS330, and today we'll be talking about a graphical model perspective on multitask and meta-reinforcement learning. 1 second, does that work? Yeah, okay. All right, so the plan for the lecture is as following. First, we'll go over variational inference, and I think Chelsea went over it a little bit already, so this will be, we'll go over it again to make sure that you understand the intuition behind it. Then we will present a framework that allows us to frame a control problem as an inference problem in a specific probabilistic graphical model. Then we'll apply variational inference to that model. And then finally, we'll get to the point where we can derive a new meta-reinforcement learning algorithm using all of that knowledge and applying variational inference to slightly different variational inference to a graphical model. All right, so a quick disclaimer. There will be quite a bit of math in this lecture and quite a bit of derivations. I want to go through all the derivations in detail. I'll skim through them and try to give you the intuitions. All the derivations are there in the slides, so if you'd like to derive it yourself or just check how it's derived, you can take a look at that. I will try to make sure that there are some anchor points, so even if you get lost, you still can kind of get back to it and get the intuition behind the ideas. If there are any questions, I think the best option is to raise your hand rather than using the chat. The chat can be a little distracting, so I would encourage you to do that, and I'll also ask every now and then after every section if there are any questions. Another thing is that this is an active research topic. There's a lot of development going on in that subfield. So there might be more questions than answers, but that's one of the reasons why this is quite exciting. All right, so let's start with why variational inference. Why should we care about this? So variational inference is a main tool that helps us cope with latent variable models. So then the natural question is, what are latent variable models? And to introduce this, I will go through a quick example. So here we plotted some kind of data distribution, right? So this is two-dimensional data, and here I color-coded it in a certain way. And this is just for your convenience, but this is the data we get to see. And looking at this data, it's not very conveniently distributed. It's not that you can easily fit a Gaussian to it and it will just work. So there might be some latent structure that might help us to model the data better. So in particular, we can look at that color encoding, which suggests that maybe there are 3 Gaussians. Maybe this is a mixture of 3 Gaussians. So if we kind of discover that fact, that there is some underlying structure, that there are 3 Gaussians, that will not only help us to model the data a little bit better, but it would also tell us a little bit more about the structure of the data we see. So now if we use the fact that there are 3 Gaussians here, we can write the probability of a data point as the sum over additional latent variable z. So that latent variable here is a discrete random variable. It's a categorical random variable that tells us which cluster does the data belong to, right? So it can only take values 1, 2, or 3. It gives us the number of the cluster. So now in order to compute the probability of a data point, what we can do is we can sum over all the clusters, sum over z, and maybe I'll use the laser pointer right here, sum over z, and we can take the probability of the data belonging to a particular Gaussian, to a particular cluster. So what's the probability of the data point given that you're in a particular Gaussian? So that would be, for example, that one, times the prior probability of which cluster the data is in, right? So to say a little bit more what that P of Z is, if we were to plot the distribution, it might look something like that. So it's a discrete categorical random variable that can be distributed like this, for instance, and this just tells us what's the probability of the data point belonging to a specific Gaussian. This is the prior on that. All right, so I hope this is relatively clear. So how can we extend this concept such that we don't just operate on discrete number of clusters or a latent variable that is a discrete variable, but instead we expand it to a continuous variable, all right? So let's try to do this. So I'll change the distribution a little bit. So now our distribution is over a variable that is just one dimensional. So we only have x here. And this is our probability distribution P of x. So it's a little funky looking distribution. And it's not very conveniently distributed. It's not just a Gaussian or something like this. So we need to represent it somehow. So now P of z, instead of being a distribution over a discrete random variable, would be a distribution over a continuous random variable, for example, a normal distribution. Right? So this will be a Gaussian. So that P of z over here, this is the equivalent just in the continuous world of that P of z that we had over here. So now if we were to rewrite that formula, it would look very similar, but instead of summing over the discrete number of clusters or discrete number of values that the latent variable can take, we would be taking the integral over all the values of z. Right? That's what makes it a little tricky. So now, what's the intuition behind it? What does that mean in practice? So if we were to sample a particular z, for example, let's say that one right here, that would correspond to some kind of Gaussian, the same as, you know, that z corresponded, let's say, to Gaussian number 1 over here. So that will get transformed to some kind of Gaussian P of x given z, right? And that Gaussian would look maybe like this. Now, what that integral is doing is it's integrating out z, so it's taking the integral over all possible values of z. For example, you know, these are a few samples, and each one of them can be mapped to a slightly different Gaussian. Like for example, something like that or something like that. And there could be right next to each other. Sorry, this is a terrible picture, but I hope you get the idea. And if we integrate out z entirely, we should be able then to represent any continuous distribution, right? We are just integrating z out, so we are integrating over every single possible z. So it's kind of like creating a mixture of Gaussian where you have infinitely many components, as opposed to just 3 components on the left. All right, so going back to why this is useful. Well, so I think you've heard about the variational autoencoder. So variational autoencoder is one use case for this, where we can have our data, for example, images, and we want to discover some kind of latent structure in the data. So what the variational autoencoder, which is a latent variable model, would allow us to do is to map our images into some latent space. So 2 points in some latent space, that could be 2 points on that Gaussian. And then we can interpolate through that latent space, and that interpolation would result in a smooth interpolation in the image space as well. Right? So we discovered some kind of latent structure in the data, and we can then generate the data using that latent structure. All right, so this is a little bit about latent variable models. So why are we talking about this in the context of control? So they're actually very common in control, and one particular use case is a Kalman filter. And Kalman filter is something that is used very often in robotics to this day to do things such as state estimation or localization. And it's a very popular approach that is actually quite old. It was discovered in the 60s. And Kalman filter hinges on a model, a graphical model that looks more or less like this. It's a hidden Markov model where we observe some variables. So in this case, we are observing, for example, the measurements. Right? So for example, your robot has some kind of LiDAR on it, and based on this, it observes the world around it. And then Kalman filter tells us how we can estimate the state or the position of your robot. So these are the latent factors Z. And so this is one possible use case of latent variable models in control, and we'll learn about a few more. All right, and then we'll also talk about control as inference, and this is a slightly different topic. So let me try to introduce it as well. Why this is important. And this is a framework that allows us to describe a stochastic optimal behavior. Right? So what do we mean by this? So far, our algorithms, our reinforcement learning algorithms, the only thing they were focusing on was to optimize the sum of future rewards. Right? So they're just trying to be optimal.
So what does that mean? So for example, if we have an owner and a dog, the dog is the agent. If the owner is asking the dog to come over, then and we observe the data, how the dog is coming to the owner, it would look probably like that. So we will have a dog here, we will have the owner here, and then the owner is asking the dog to come over, and let's say the reward is the distance to the negative distance to the owner, and then the only thing that our reinforcement learning framework can explain right now is the straight path, right? The perfect optimal behavior, because the agent is only optimizing for the sum of the rewards. However, we know that in the real life, dog can actually take a few different paths. Maybe it will look something like that, where maybe it will sniff something on the side, maybe it will get distracted, and it won't be always perfect. So it's optimal, but it's a little stochastic. Right? So that's also how we humans do things. We're not always exactly perfect, and we're not always exactly optimizing some kind of reward, but you kind of can get from our movements what we were trying to do, but our behavior is a little bit stochastic. So the idea in control as inference is that if we can describe that stochastic optimal behavior through some model, and then transfer this to our agents, maybe our agents would behave a little bit more like we do, and maybe it will improve our reinforcement learning agents. And that turns out to be true to some extent. So we'll learn in the future lectures on how the probabilistic graphical model that we'll use to describe control can help with better exploration, with hierarchical reinforcement learning, and skill discovery. All right, so this is a short intro to the topic. We'll jump into variational inference now. Are there any questions? All right, looks like no questions so far. Okay, so let's talk about variational inference. So variational inference is a tool that allows us to deal with these latent variable models. And just to repeat, what's the problem with the formulation that we have so far? Well, the problem is that, so this P of Z, this is just a simple normal distribution. That's a Gaussian. Gaussians are nice. We know how to deal with them. This P of X given Z, it's also a Gaussian, for example, a Gaussian right here. That's relatively easy as well. But what's difficult, what makes that entire equation difficult, is that integral over a continuous variable. That makes it intractable. So we need to somehow get our Z's, but do it without the integral. And this is where variational inference comes in, where it can be useful. All right, so I'll go through this relatively quickly. Let's see how we can go about it. So usually we will try to, what we are trying to do in supervised learning, we're trying to maximize log likelihood of our data. All right, so here we are, we have the ith data point. I depicts the index of the data point. We are having the ID assumption of our data, and we are multiplying the probabilities of our data belonging to the model, and we're trying to maximize that. And then we can do this with log likelihood instead, since logarithm is a monotonic function. All right, so far so good. So let's now take the log of p theta of xi, so the log probability of a particular data point xi, and let's write it out according to our model. So according to our little integral right here. All right. So let's move a little further. Now we can multiply that entire equation by 1. We can always do that. And here we pick a particular version of 1, which is some kind of distribution of z, of our latent variable. We'll call it qi of z. And we will divide it by the same thing so that it's just 1. Right? Now, an important thing to note here is that this could be any distribution of z. Right? We just picked some qi of z. It could be anything. It could be q of z given something. It could be just q of z. The options are endless here. All right. So now what we can do is we can take that qz, and we have an integral of qi of z dz, which is the definition of the expectation under qiz. So this is what we did right here. We still have the log, and instead of the integral and the qi of z in the numerator, we have the expectation. Now we can apply Jensen's inequality, which is a simple inequality that tells us that a logarithm of a logarithm of an expectation is always greater or equal than the expectation of the log. Right? So we are not going to prove it, but it basically looks like this, and we can actually derive what that bound is, and that's
that's not that complicated. I can include it in the lecture notes, but let's just keep going and see where we get with this. So right now we are lower bounding our objective by something that looks like the expectation of the log of that ratio. Now we can split that ratio into two different terms, which we did down here. And we can split it even further and say that our log p theta of xi is lower bounded by something that looks like this. By log of p of xi given z under the expectation of qi of z, minus the KL divergence between qi of z, so some kind of distribution that we just made up, and the prior p of z. All right, so this is a very quick derivation, but let's just focus on that formula and try to understand what that means. All right, so here I just copy pasted that final equation. And just one quick note. So what we did here, if we look at this, we said that I is the index of the data point. So xi is a particular data point in your data. So far we introduced qi of z, which is a distribution over z that is specific to that particular data point. All right, so we have qi of z here and qi of z here. So what that means, we'll have as many distributions, q of z distributions as we have data points, which is, in the era of deep learning, this is a very, very large number. So we don't necessarily want that. So instead, what we will do is we will use so-called amortized variational inference, which changes the distribution q, and rather than it being qi of z, it becomes q of z given xi. And so we are free to choose whatever distribution over z we like. We chose that distribution so that instead of having many distributions, we just have one distribution that tells us the z given the current data point. And so this is a small modification. All right, so let's take that formula and let's try to understand the intuition behind it. And here, one last thing to note is that we would have two different parameters here. We will have parameters for our p distribution, and these we'll call parameters theta. These are the parameters that, given our z, would tell us would tell us the probability of the image. And we have parameters phi, which are the parameters of our variational distribution q. All right, and we can use that equation. We can maximize that variational lower bound, so-called, to optimize for both of these, for phi and theta. All right, so intuition. All right, so what we built actually looks something like that. We have our input data point xi. Then this gets transformed into some kind of latent code using our variational distribution. Right, so we'll have some kind of neural network that takes that data point and then transforms it into some lower dimensional latent space z. All right, and this is our q phi of z given xi. So in other words, this is encoding the image into some kind of latent code z, right? We can also call it the encoder. And then we have the second part of that equation, which now takes that latent code, samples from that distribution, takes that latent code and produces the image, right? So this is now p theta of xi given z. So this is trying to decode that latent code back into the image. And so this is variational autoencoder, where we are first encoding the image and then decoding it. All right. So this is the equation. This is the variational lower bound that we just derived that we have to maximize with respect to both theta and phi in order to learn that. And usually we have that little term p of z here that we haven't talked about. Usually what we pick for this is just a standard normal distribution so that the KL divergence is fairly easy between the two. And in general, that doesn't lose generality for the entire variational autoencoder. And that would allow us to get to the use case that we talked about, where we can have two images mapped to different parts of the latent space, and then we can interpolate through that latent space z, and different samples from that space would result in different images from our data set. All right, so what does that mean exactly, that equation? It looks a little complicated. So what's going on here? So there are two terms here. There's the first term right here, which is that expectation under Q5Z given Xi. So this is expectation under our encoder. So it just tells us, given the image, what is the most probable Z that would have produced that image. We are trying to reconstruct that image, right? We're trying to maximize the log likelihood of that image given Z. So that means that we are trying to, we can call it the reconstruction loss. And this is just trying to encourage the distribution to describe the input, right? So it will be pushing both Q of Z given Xi and P of Xi given Z to just describe the input as well as possible. So if we just look at our Q, what our Q will be able to do is it will just try to find such a code Z so that the reconstruction is as easy as possible. So Q is trying to help P as much as it can. Now, what can happen if we just use that first term only is that our Q can cheat a little bit, and it can just have a very tiny distribution, basically a Dirac's delta, and say that for that particular code, this is the image, right? So it's a perfect encoding, but it's not necessarily what we are looking for. We are trying to look for a distribution that is a little bit wider so that we can sample from it and so on. So that purely that encoding objective, that reconstruction loss, can result in something that we don't necessarily want, in a way that, in something where our variational distribution can cheat a little bit. So in addition, then we introduce this additional term, the DKL term, the KL divergence between our variational distribution and the prior. And this is penalizing the KL divergence, which kind of acts as a regularizer. So because our P of Z is a normal distribution with a certain variance, we are trying to make sure that the KL divergence between our Q and that normal distribution is as small as possible. So basically that means let's keep that variance of our variational distribution a little bit larger so that we can describe more inputs, so it's a better regularizer. It prevents our Q distribution from cheating. All right, so that was a little bit of intuition behind variational inference. Are there any questions?
One question that came up in the chat is like, how do you represent distributions over Z and for X given Z? So one choice is Gaussian, which is typically the normal choice. Are there other choices?
Yeah, in variational autoencoder, as far as I know, people use Gaussians. I think there are other distributions that you can use. There's one little caveat that we haven't talked about, which is how do you backpropagate through all of this? And this is by using so-called reparameterization trick. And there are certain distributions that we know how we can do reparameterization trick with, such as Gaussians, it's fairly easy, and such as some discrete distributions. So some people use discrete distributions there too, but I think Gaussian is by far the most popular choice.
There's another question. Why do we always choose the standard normal distribution for P of Z?
Right. So that's a little bit of a design choice, but our P of Z can be, it kind of doesn't matter what it is, because our, if we go back a little bit here, let me just show the pointer. Our P of Z can, let me switch to this. Okay, our P of Z can be any distribution. And then if we have a neural network that can map from Z to P of X given Z, then our neural network is expressive enough to take a sample from any distribution and transform it to any other distribution we would like. So it kind of doesn't matter what P of Z we'll choose. Neural network is powerful enough to represent anything else after that. So usually we try to pick something that is really easy to deal with, such as a normal distribution, the KL divergence is given, and things are very well understood, because we don't really lose much. The expressiveness is still there because our neural network will be able to transform it into P of X given Z. All right. So let's go into, let's kind of put a pin in this in variational inference. We'll get back to that method. But now I would like to introduce control as inference framework. And this is the framework that we briefly introduced, and this is a framework that allows us to describe a stochastic optimal behavior. So we had the dog is trying to come to the owner, and we just don't want to have the only behavior being the straight line, but we also want to be able to represent behavior that is a little bit stochastic. Right? And when we deal with stochasticity, we usually want to introduce some random variables and potentially a probabilistic graphical model. So let's do that. So the things we know are that there are some states and actions that the dog can do, right? So we can write a very simple probabilistic graphical model where we basically represent the dynamics of the world, and we say that there are some states, there are some actions, and the dog can take an action in a state, and that will lead to a different state. Right? So that just represents kind of all the behaviors that the dog could do. And we will now represent the joint probability distribution of all the states and actions as P of tau. So tau represents a trajectory. So this is a probability distribution over trajectories. And this is not really very expressive because, actually, before we go there, so what we assume here is that we have the transition model P of S prime given S comma A, right? So we know how the dynamics propagate. Now, this is not extremely expressive because this just describes kind of any behavior that the dog can do, right? The dog can take any actions that will result in next states, but it doesn't really describe the situation that we're in right here, where the dog is doing a very specific behavior, right? The dog is very intentional. It has a task that it has in mind, and it's trying to reach the owner. So we'll introduce an additional random variable that tries to describe this, right? And this would look a little funny. This is a random variable that is a binary random variable depicted by this script O, which stands for optimality, which is a variable that basically represents the intentionality of the dog, right? So the dog is trying to accomplish a certain task, and it's not just doing random things, right? So we'll introduce it as a binary random variable, so it can take only true or false as its values. And if it's true, that means that the dog is trying to be as optimal as possible. And if it's false, then the dog doesn't care about the task. It's just the optimality doesn't matter to it. All right, so now we can represent the probability of the trajectory given the fact that the dog is trying to be optimal. So given that our optimality variable 1 through capital T is equal to true. There is one point that is missing in this. We introduce an additional variable that we assume to be no. We assume that the dog is always optimal. So we'll always, if we say that we have probability of the trajectory given O, we'll assume that the O is equal to true, right? So optimality dog is trying to be optimal. But we introduce this additional random variable, and we didn't really describe what those connections mean, right? What's the dependence of that variable on the action and the state? So we'll also introduce this, and we'll introduce this as following. We'll say that the probability of the dog being optimal at time step T, given a state at that time step and the action that the dog took, is equal to the exponential of the reward at that state and the action, at that state with that action, right? So the dog is basically exponentially, what's the best way to describe? So basically, if the higher the reward is, we will exponentiate this, and our optimality will be proportional to that. So the dog is trying to be more optimal as it's getting more reward, and that scales exponentially. Right? So this might seem a little funny right now, why there's an exponent here, but this is a particular design choice that we choose so that we arrive at the algorithm that we want at the end. All right. So this is the graphical model that we introduced to describe a stochastic optimal behavior of that dog that is intentional. I would like to do a little sidestep, and we're dealing now with a probabilistic graphical model that has some variables that are observable, such as optimality, and some that are not known. And this looks like a hidden Markov model that we briefly mentioned. So I just wanted to do a little recap of hidden Markov models and briefly describe how they work. So hidden Markov models are models that look like that. So we have some kind of evidence that is given to us. And there are some latent factors that we don't get to see that we would want to estimate. We would want to infer what they are. And one instance for this is, for example, in a Kalman filter where we are getting some kind of measurements and we're trying to estimate the positions of the robot. And we know that given that we are in a certain position, we can be in the different position in the next time step. And we also know that given that we are in a certain position, we should get a certain measurement. All right, so what's usually assumed to be known here? First, we assume that we know so-called emission probability. So what's the probability of our measurement given the latent state? So this is also often known as the observation model in the Kalman filter. We also assume that we know the transition dynamics. So we know the probability of zk given zk minus 1. And then we also assume that we know the initial probability distribution z1, p of z1. All right, so usually what we are trying to do in hidden Markov models is we are trying to estimate this quantity. So what's the probability of our latent variable at time step k, given everything that we get to see? So given all the measurements 1 through n. Right? So if we're able to estimate this, then we can do inference about any z. Right? So this is the goal for our inference, what we're trying to do. And there's one particular algorithm that is trying to do this. And this is a so-called forward-backward algorithm. Now I'll just very briefly tell you what it's doing, and then we'll use it for our probabilistic graphical model. All right, so forward-backward algorithm consists of 2 steps. There is the forward step, which is trying to compute this quantity, which is the probability of our latent at time step k, given all the measurements up until that point. So given all the measurements x1 through k minus 1. And then there's a backward algorithm that is trying to compute kind of the opposite. So it's trying to compute the probability of our measurements from k through n, so from now till the end, given our latent variable zk. All right. So you might ask, why does it look like this? Why do we compute these particular quantities? And the reason is that if we're interested in this quantity right here, p of zk given x1 through n, we can show, there's a little bit of derivation here, I'll skip that, but we'll skip right to the answer, and we can show that that quantity that we're interested in is equal a product of both of these probabilities. Right? So if we are able to do the forward pass and the backward pass, then we will be able to find the answer to our question that we're interested in. All right, so this is a little sidestep into hidden Markov models.
There's a question in the chat asking about the arrow between from z to x, whether it should be from z to x or whether it should be from x to z.
Shouldn't there be arrow xn to zn? I'm not sure I understand the question. Could you repeat that?
So I think that they're, you could also speak up if you'd like. I think that they're asking in the graph.
Yeah, I can skip. So I wanted to ask if the arrow should be x1 to z1, because x1 is observation here, right? And from the observation, you arrive to the latent space, z1.
Right. Yeah, so I see. So it's about the direction of this arrow right here.
Yeah.
Yeah, so in that model, the reasoning is as following. There is some underlying state that is the true state that gives rise to some measurement, right? It's not that the measurement gives rise to where you are at. It's rather that you are at a certain position and that would give rise to a certain measurement. So kind of causality works this way rather than the other way. Does that make sense?
Yeah, it is. Thanks.
Okay, great. All right, so we have our hidden Markov model side note. So let's try to look in particular at the backward algorithm, and let's try to apply it to our case. So in this case, we are trying to estimate the probability of our evidence of the things we know, x, k through n, given our latent at the current time step. Right, so we go back to our model. Here in the top right corner, I described everything we know about it. And now we will we'll denote the backward message as beta of st, at. And this would be equal what we know from the current time step till the end. So from small t through capital T, given the latent at the current time step st, at. Right? So what that depicts is the probability that we can be optimal at time steps t through capital T, given that we take action AT in state ST. All right, so this is our backward message, and we can go through the backward algorithm and compute this. And I'm not going to go through the derivation, but I'll show you the final result. And the final result looks like this. We will arrive at a recursive algorithm that starts from the end. That's actually where the backward name comes from. It's a dynamic programming algorithm, and it computes the backward message like this. It uses the probability of optimality given the current state in action, and then the expectation under the current dynamics of the backward message at the next time step that is only dependent of ST plus 1. And here we define what that backward message that is only dependent on ST is equal to. So basically, if you do dynamic programming and you go backwards, at this point you would already know what that is, and we know what that is. This is given to us. So we should be able to do the entire backward pass using these formulas. All right, so I wanted to look a little bit closer at what this actually means. So we went through this backward algorithm, for this backward pass, and we arrived at these two quantities, and they're maybe it's not entirely clear what they mean. So let's do a little assignment, and I'll introduce a new letter, VT of ST, and I'll say that this is equal to the log of beta of our backward message that is dependent only on the state ST. Right? We know what that beta of ST is. We just define it right here. We just derived it right here. And then I'll introduce another letter, QT of ST, AT, and I'll say that this is equal to the log of the backward message that is dependent on ST and AT. So this is what we derived right here. So this is kind of a random assignment that I just made up. Let's try to run with it, and let's try to replace that equation with that assignment and see what we get. Or actually, sorry, let's try to start with this equation right there. All right, so if we do that replacement, we'll end up with something that looks like this. Our VT of ST is equal to the log of the integral of the exponential of QT of ST, AT over all the actions AT. Right? So that looks a little weird, but somewhat close to Q-learning, where the value function is very closely related to the Q function. So if we assume that our V is kind of like a value function and the Q is kind of like a Q function, these two seem kind of related here. But we have that little term here that is a little complicated, this log of integral of exponential. Right? So what is that term? Let's try to think a little bit about this. So let's try to consider a situation where our Q values are really big. Right? So we have really big Q values. So for any different action, the value there is really big. Now we will exponentiate all of them, right? So if we exponentiate every single one of them, and these are really big values, then the difference between them will get much, much bigger, right? Because of the exponential function. So if we do that, then our biggest action will be really, really big, even compared to the second biggest action, right? So then we'll take the integral across all of these actions. So we'll kind of sum over all the possible actions, and that sum will be now dominated by that top action, right? By the action that had the biggest Q value. And then we'll take the log of all of this. So basically, if that sum is dominated by the exponent of the highest for the Q value for the highest action, if we take the log of this, we are going back to the Q for the highest action. So basically, we can say the following: this log of integral of exponential is basically a max over actions of our Q function as Q function gets bigger and bigger. Right? So the bigger the Q is, the more it looks like this. All right, that looks somewhat familiar now. So let's take a look at the second equation. Right? So again, we have this equation that we got from the backward pass. Then we have our assignments that I wrote down here. Let's try to transform this. And if we do this, we will end up with something that looks like this. We would have our Q function of ST80 is equal to the reward at that time step, plus the log of the expectation, this is expectation under dynamics, of the exponential of VT plus 1 of ST plus 1. All right, so this kind of almost looks like the Bellman equation. So let's try to make it a little bit more into a Bellman equation. So this is the expectation under our current dynamics. So let's pretend that the dynamics are deterministic. So there's no expectation, the expectation of a constant, we can remove that. So then we have the logarithm of the exponent, right? So these two cancel out, and we'll end up with, for deterministic transitions, we'll end up in an equation that looks like this. Our Q is equal to the reward plus the value at the next time step. All right, so now this looks very familiar. Now, there's a little bit of a problem because we just got rid of that expectation here, and there's something a little bit off about this, but we'll come back to that stochastic case a little later. All right, but for now, we saw that with that specific assignment, we can kind of retrieve something that looks like a Q-learning algorithm where our Q is equal to the reward plus the value of the next time step, and our value is the max over actions of the Q. All right, so let's go one step further. And so far, we just computed the backward step, and we kind of arrived at something that looks like Q-learning. Let's try to compute the policy. All right. So with the policy, we'll try to compute the probability of action at the given state, assuming that we are optimal. Right? We'll depict it as pi of AT given ST. And I'll skip the derivation. We apply Bayes' rule here, but at the end, we arrive at something that looks like this. Our policy is equal to the backward message that is dependent on ST given and AT divided by the backward message that is only dependent on ST. All right, so let's try to put all of this together. So first, we have our backward pass formulas that look kind of like Q-learning. And now we have our policy that is equal to the ratio between these two backward messages. Now, if we use our assignment that we had before, we will arrive at something that looks like this. Our policy, so our probability of action at a given state, is equal to the exponential of the Q at that state for that action minus V at that state. So this is the difference between our Q function and the value function, which is also known as the advantage function. Right? So now we said that our policy is equal to the exponential of our advantage for that specific action in that specific state. And that seems to make sense. So basically what it says is that the policy, assuming that you're trying to be optimal in that probabilistic graphical model, will try to pick actions that are exponentially more likely or exponentially give higher advantage. Right? So like the higher the advantage is, the exponentially more likely we will be to pick those actions. And importantly, we won't be picking the actions that are always optimal, right? That we are not just taking the actions that are doing the max over the Q, but we are doing something that is almost like this. It's a little bit softer, right? And they're distributed according to this distribution, and that distribution is very tightly tied to the reward, but it's not just the max. All right, so this is quite a bit of math in control as inference. I was trying also to give you a little bit of intuition, but are there any questions at this point?
I did have a question about the backward pass, and in particular the big T. I didn't really understand how this algorithm gets off the ground running, because maybe you could just explain first what big T is. But yeah, if you look at the first, like when we first start the dynamic algorithm, we need some value at T plus 1, right?
Right.
Maybe on the next slide.
Next slide.
Yeah, the first line under the for loop. Like when we first start the algorithm, we have to have the expectation there of beta T plus 1, but how do we get that to begin with?
Right. Yeah, this is a great question. All right, so actually to explain this, we would need to go back here. So here what we would have is we would have a node at the end that would be S, well, capital T, right? And I believe we would also have the optimality variable at that time step O at time step T. I believe that's the case. Let me think about this. Yeah, I think so.
So I think at the very, I'm not entirely sure about this. I can get back to this for you. I'm sorry. But I believe that at the very final time step at t-1, this quantity here that is in question will be equal to, so we will have the backward message of bt plus 1 of st plus 1. That bt plus 1 of st plus 1 would be equal to something like that. So the question is basically, what would that be equal to for the very last time step? And I believe this would be the probability of the optimality at the very final time step given state and the action, and that will be just equal to this exponential of the reward at the very final time step. So for the very final time step, it would just equal to this. And then we would go backward from there, I believe. But I can double check that for you.
And t is in the future, and it's defined a priori. Big T is in the future, sorry, and it's...
Right, so t is kind of the horizon for how long the dog will be acting.
Okay.
Right, so the t will be the very final time step where the dog kind of gets to the owner and it stops there.
Okay, cool. I think I kind of get it. Thank you.
Okay. All right, cool. So we talked a little bit about control as inference. Now we'll take the concept that we introduced in the first part of the lecture, the variational inference, and we'll try to apply it to our problem and see where we end up. All right, so we started with a graphical model that looks like this, and we can write the joint probability of that entire model. And what we know is we have the initial probability distribution of the initial state. We have the transition probability, and we also have the probability of optimality for the given state and action. This is the exponent of the reward. So we know that our joint distribution, given that graphical model, would factor like this. It factorizes like that. All right. So this is what we know so far. Now we will try to introduce a variational distribution. So variational distribution is a distribution over things that we don't know, that are not visible to us. So this is not over the evidence. The evidence in this case are our optimality variables. So the variational distribution, or Q of Z before, has to be over the things that we don't see, right? So this would be the Q of S1 through capital T, comma A1 through capital T. And we'll just say that our variational distribution is of this form. And we pick this particular graph with certain goal in mind, and you will see that in a second. Right, so this is a graph that looks very similar to the graph we had before. Right, it's very, very close, but it has this one additional connection between S and A. Right, and usually we try to pick variational distributions that are very simple, so that all the equations get simpler. Here we made a little bit of an odd choice, but we will see that it will actually allow us to make things simple at the end. All right, so let's talk a little bit about this graph. So here we have the probability of the initial state is the same as what we had before. We have transition dynamics that was also described with the exact same probability as before. But here we introduce an additional connection, and this is the variational connection that we didn't have in the previous graph, and we'll call it Q of AT given ST. Right? So now we can write the entire joint distribution for that graphical model. And this would be equal to probability of the initial state times the product of all the transition probabilities and our Q of AT given ST. Right? So now we have our variational distribution and we have our original distribution. And one thing to note here is that the variational distribution has the exact same dynamics and the initial state as P, as our original distribution. And the only new thing is this variational distribution Q of AT given ST. Right? So this is the choice we made for our Q. All right, so now if you remember, we were operating on X's and Z's before when we were talking about variational inference, where X's were the things that we know and Z's were the latent factors. So here we'll do assignment that looks like this. We will say that the things we know are our optimality variables. We assume them to be true. And the latent factors are all the states and actions.
So in that case, that joint probability distribution down here is Q of Z, and that joint probability distribution right here is the probability of Z comma X. Right, since Z is everything here and X is that part. All right, so let's try to apply our variation lower bound. So this is a quick reminder of variation lower bound that we had at the beginning of the lecture. And let's try to apply it here. So the variation lower bound looked like this. We can transform it a little bit to look like that. All right, so now we have that log of P is lower bounded by this formula right here. So let's try to apply it given our assignment that we set. Right, so if we do that, then we have our joint probability distribution of P of X comma Z, and we have our variational distribution Q of Z, or Q of S1 through capital T comma A1 through capital T. We will now do the assignment, and so we will say that log probability of our optimality, 1 through capital T, is lower bounded by the expectation now. The expectation is under the Q, and our Z is our joint probability of all the states and actions. And now we'll take that log of P of X comma Z, and we'll apply the rule that if you take the logarithm of the product, you will get the sum of the logarithms. And it would look something like that. So basically we would have here, we're describing the log of P of X comma Z, just using our assignment, right? We're just basically splitting that product into the sum. And now we have to subtract our log of Q of Z. So let's do that. So this is our Q of Z. We are applying the log rule and we're splitting it into a sum. So now you can see that this log of P of S1 is equal to this. This part is equal to our product of transition dynamics. And then we have one additional term, log Q, AT comma S, given ST. Right? And now you can kind of see why we made that odd choice at the beginning. What that allows us to do is that allows us to cancel out the initial state distribution as well as the dynamics. So what we end up with is something that looks like this, and in particular, something that looks like that. So our optimality, the log probability of optimality, is lower bounded by this objective. So if we're trying to optimize our optimality, since this is lower bounded by this, we can instead maximize that lower bound, and that will result kind of in the same thing. So what is that lower bound here? That lower bound says that we'll be taking and we'll be summing over time steps under the expectation of our current Q, all the rewards that we're getting at every time step, plus the entropy of the policy Q of AT given ST. Right? So what that means is that if we're trying to be optimal, in order to do this, given that probabilistic graphical model and that variational inference, we will be optimizing the rewards, but not only just the rewards, which is what we would do in the standard reinforcement learning, but we will also add to that objective the entropy of the policy. So what that means is that the policy is trying to stay as wide as possible, right? So it's trying to not be committed to any solution, it's trying to be wide. So what that translates to is that we're trying to maximize the reward and maximize the action entropy. All right, so to quickly summarize this, our objective from that variational inference in this graphical model looks like this. It's the sum of the rewards plus the entropy. Then we have the value and Q functions that are also derived using that same framework. And actually, if we apply that variational inference that we just described to our Q function, it will result in something like this, which resolves our problem that we had before, that expectation right in the middle here. So this problem is gone if we do this correctly. And our policy itself would be exponential of the advantage. Right? So we have kind of all the components that we would need to construct an algorithm now. So if you remember the Q-learning algorithm, it looked like this. We were collecting a data set, then we were calculating the target values for the Q function, and this was equal to the Bellman equation, so it was the reward plus the maximum of the Q at the next time step. And then we were trying to fit our Q function to these targets. Right? This is a standard Q-learning algorithm. And we saw an application of this, for example, for QTOpt for robotics. And our policy was picking the max, the argmax of the Q. So it was picking the action that maximizes our Q value.
right? So here we derived something that we'll call a soft Q-learning algorithm. Since the max is not just a pure max, but it's a little bit softer, we kind of incorporate the stochasticity here. So far, I just copied everything that we had on the left side. So here are the modifications. So the Bellman equation is changed as following. Instead of having the hard max over the actions, this is changed into a soft max, and soft max describes the log of integral of the exponent. Right? So we are not taking the full max, but we are a little bit softer here. And instead of taking the policy that is doing the argmax over the Q function, our policy is now the exponential of the advantage, right? So it's not as hard as before either. All right, so we started with some probabilistic graphical model that describes stochastic optimal behavior. And then using backward messages and a little bit of algebra and variational inference, we derived an algorithm that resembles Q-learning, but it's a little bit softer, that kind of takes into account the fact that we are trying to be a little bit more stochastic. All right, so let's quickly see how this algorithm works in practice. So this algorithm was implemented in this paper from Thomas Hornoy et al. And just to, again, give a little bit more intuition, if this is the landscape of our Q function in gray here, so on the y-axis we have the Q value, on the x-axis is the action, and the Q function has some hills and valleys. Usually if we were to apply a standard Q-learning algorithm, our policy will basically focus on the peak of that Q function. Right? That will always try to pick the max here. With soft Q-learning, our policy is now proportional to the exponent of the Q, or the exponent of the advantage. So it's not only trying to put all the probability mass at the peak, but it will save a little bit of probability mass for other hills as well. So it's not as committed as the standard Q-learning algorithm. Right? So this is kind of the motivation for it. Right. So why is this useful for the policy to not be as committed? So here are a few examples. So first, this is useful for exploration. So here's a task where you have this ant-like robot, and the robot starts right here, and it's trying to minimize the distance to the goal, which is that blue square right here. Now, if the Q-learning, on the left, we see the behavior of a converged Q-learning algorithm, where the ant just happened to explore the path up here first. And since this is also initially getting smaller and smaller distance, it gets a little bit stuck here. And the policy is basically like always looking for those hills for the hill in the Q function landscape. So it's really difficult. The policy has already committed to that solution, and it's really difficult for it to unlearn it and try something else. On the right here, we see a solution coming from a soft Q-learning algorithm where you're not as committed. You still have some probability mass on actions that might have a little bit a little bit lower outcome, but that allows you to kind of keep exploring different options and eventually find the better solution to the problem. This is also shown here, where the reward is just the speed of the ant, and the speed can be in any direction. So basically just the speed. And on the left here, we'll see what's the distribution of behaviors that we get if we do a standard Q-learning algorithm, such as DTPG, which is a specific actor-critic algorithm. And what is the distribution of behaviors we get if we apply soft Q-learning to that problem? Right, so let's see. So you can see that DTPG kind of seems to be committed to one direction and it just goes with that. Versus soft Q-learning allows the ant to kind of explore all kinds of different directions and cover the state space a little bit better, because it's also trying to optimize for that entropy of the policy. Okay. So what that also means is that if we were to pre-train our policy with soft Q-learning, it will be much easier to fine-tune, because now our ant is a little bit more competent. It knows how to behave in many different conditions. And lastly, that also leads to more robust policies, right? So here's an example of a real robot experiments where the authors are trying to stack these two Lego blocks. And because this is trained with soft Q-learning, now if you perturb the robot, the policy has visited these states because it was not trying to be very committed and just straight optimal.
and it knows what to do with them. So it's a little bit more robust. If you perturb it, it might have experienced that state during training because it wasn't as committed, and it knows how to get to the goal. All right, so this summarizes control as variational inference framework, and we introduced the soft Q-learning algorithm. Are there any questions at this point? Oh, and I think raising a hand.
Yeah, would you mind go back by 2 slides?
Yep.
Yeah, so just curious, what is the softmax term that you add to the second line of the soft Q-learning algorithm? So because you don't have access to that AI prime, that action.
Oh, sorry. So this is over all the actions, right? So the softmax term is exactly this, right? So you're taking the log of integral across all the actions.
Oh, okay.
It should be dA. Right.
Okay.
So before we were taking the max over all the actions. Now we are taking softmax, and softmax is a term for this little equation here, the log of integral of dx.
Okay, thanks.
Yep. There's another question.
Yeah, I just was wondering, when we made the assumption about the probabilistical graphical model that enabled us to kind of cancel out the dynamics, are there any practical limitations to that, like that would limit the learning of the algorithm?
That's an interesting question. So to rephrase this question, is it possible to come up with a different variational distribution that will make the algorithm better? Yeah, that's really interesting. I'm not sure. Potentially. I haven't thought about other variational distributions that we could do there. There's many different options. It just has to be any distribution over the variables that we don't see, over latent variables. This particular one gives rise to this algorithm, but I think there are probably other options, and that could give rise to different algorithms. I'm not sure, but this is a very interesting question.
Thanks.
Yep. All right. If there are no other questions, then let's take all of this that we derived so far, and let's try to introduce a new meta-reinforcement learning algorithm using all of these tools. All right. So far we've been considering the dog and the owner, and the task was very clear to the dog. Right? The dog was trying to get to the owner, and it was getting there in a stochastic way, and we're trying to describe that process. So now with meta-reinforcement learning, the problem setup is a little bit different. Now the dog doesn't necessarily know what the task is, but the owner does, right? So the owner has some kind of trick in mind that they want the dog to do, but the dog doesn't know what the trick is. Now the dog knows that if it does the correct trick, if it guesses it right, then it would get a treat. Right? So it's a slightly different situation. And my question to you is, given that setting, what's a good strategy for the dog? And you can either write in chat or you can raise your hand. But what would you do if you were the dog? I think you have your hand raised. I'm not sure if this is from the previous question, but feel free to answer if you have any ideas.
Shoot, that was from the previous one. I think I missed the question actually, but I think if the dog is being ordered to sit, or he thinks that the other person wants him to sit, then he should sit.
All right. Yeah, so the dog doesn't necessarily know what the owner wants from him, right? It's trying to guess. So, but it can't, I guess we can assume that maybe the dog can think that maybe the dog can try to guess what the owner wants. For example, maybe the owner wants him to sit, and it should then just sit. So it should just try something out. Yeah, I think that's a fairly good strategy. Learn to follow different directions of the owner. Right. So if it could understand the directions of the owner, then it should just try to follow those. But let's assume that the owner can't communicate with the dog. Right. The owner has just something in mind.
Okay, try everything with equal probability. Yeah, I think that's a really good strategy too. Yeah, so just guess what the owner has in mind and just go for it and try it. And if you get a treat, good for you. If you don't, you'll just take a step back and try something else and go for it and try that other idea that you have until you get the treat. All right, and believe it or not, that this is connected to our variational inference framework. So we'll talk about that. All right, so before we had the probabilistic graphical model that looked like this, and that described this situation where the dog knows what to do. The dog knows what the task is. So now we'll introduce an additional random variable that describes a situation where the dog doesn't know what the task is. So we'll introduce an additional latent variable z, which describes the task, right? And this is not observed. This is not part of the evidence. Now our z, our optimality will depend on this, right? Whether you get the treat or not depends on what task you have in mind. And because we introduced this z in the original graphical model, we also have to introduce it in our variational distribution. So now our policy will be also dependent on z. So depending on what you think the owner wants, you'll be trying very different actions, right? For example, if you think that the owner wants you to sit, you'll try to sit. All right, so z in this case corresponds to the latent task that the owner has in mind. Right? So we changed our probabilistic graphical model a little bit to describe that situation. All right, so we have that additional z. What will we do? Well, we'll apply variational inference again. Right? This is the tool that we know how to use. Let's try to use it. In this case, we'll change it a little bit. So before we had x's as the evidence, so as our optimality variables, and z's were the trajectory, so all the states and actions. I'll change it a little bit and say that x's are still the optimality variables, but z is the latent task. Okay. And then we had our variation lower bound that we derived at the beginning. So now let's use the assignment and see how this will change. So what will happen is here, instead of xi, we'll have the log probability of the optimality. And for now, I left the q untouched, but I just changed log of p of xi given z to log of probability of the optimality one through capital T given z. So z in this case describes the latent task. Right? So that's the only thing I did. Let's look a little bit further. What is this term? Right? So this is the probability of optimality given that you're in a specific task. So we know from the previous section that the log probability of optimality is lower bounded by this objective where we are maximizing the reward plus the entropy of our policy. So now this is now conditioned on z. So we'll change that formula a little bit, and we could go through the entire derivation, but I'll just show you what the result is. So now the log of p of 01 through capital T given z will be equal to still the sum over all the time steps. Now our variational distribution is not only over S, ST, and AT, but also over Z. So we'll change that. The reward will depend on the task Z as well. And our entropy would be on of the policy that is also dependent on Z. So the policy works differently depending on different Z's. So it's very similar formula that we had before. We didn't go through the whole derivation, but it works basically almost exactly the same. All right, so we have the other term left, which is this q of z of our task given xi. And so in this case, our xi technically should be the optimality variables, but they're not really telling because these optimality variables are always true. And if you remember, we can pick the variational distribution to be conditioned on anything we like. Okay, this is our design choice. And we would want to pick the thing that our variational distribution should be conditioned on, such that it's very easy to guess what task it is. And so the question is, what's a good xi in this case? What should we condition our variational distribution on so that we can easily guess what the task is? So in this case, one thing we can try is just to transition on all the transitions that we have seen so far. So basically, the dog is trying different tricks, and it will try to guess what task it is, given everything that the dog has done so far, right? So if it's tried sitting and it didn't get any rewards, we'll incorporate that into its thinking. If it tried, I don't know, jumping or shaking or something, it will also incorporate this. It will incorporate everything it's ever done and the rewards associated with those behaviors. All right. So this is the main idea behind Perl algorithm, and this is a way to derive it using probabilistic graphical model. And I think you've heard about this algorithm before, so I'll just quickly give you the intuition of how this works with this graphical model. So this is work by Kate Reckley et al. So Perl is an off-policy meta-reinforcement algorithm that works like this. We would have some kind of adaptation data. So this is a dog trying different things and collecting all the transitions. So the dog trying to sit, trying to jump, trying all kinds of different things. And in this paper, they refer to this as context C. So C in this case are all the transitions that you've seen so far, right? And then we'll have our variational distribution where we're trying to guess what task it is. So this is the probability of the task of Z given all the history so far or given our context. So this is basically this distribution right here, our Q of Z given Xi, where Xi is the context C. Right? So we'll take the adaptation data, we'll take everything we've seen so far, and we'll try to guess what's the most likely Z that would explain that would explain that data. And then we will pretend that this is the task that the owner wants. So we'll guess our best Z, we'll pretend that this is the task that the owner has in mind, and then we'll try to optimize our Q function with that task in mind. So we'll try to optimize as if this was the task. So it's basically equivalent to the dog trying to guess what is the task that the owner has in mind and just going for it. So if you look at the objective that the authors write in this paper, it looks exactly the same as the objective that we wrote in the previous slide with variational inference. So this is the objective where you take the expectation under our Q phi of Z given the context, or given all the transitions. Here we have the reward, and this is actually a soft reward. So this is using the reward plus the entropy. And we have the KL divergence term that tries to keep this distribution, our variational distribution, close to a normal Gaussian. So so that we have that regularization term that comes from variational inference. And then because this is, we can do all of this using off-policy reinforcement learning, we can optimize for this reward using our soft Q functions and so on. This is an algorithm that can be run off-policy, and because of this, it's much more efficient than many other on-policy equivalents, such as RL squared, MAML, or ProMP. And this is what you see in these graphs here. So it works really, really well. All right, so I just wanted to reiterate this, the intuition behind this. So if you remember, we were talking about the dog that knows that if it does the right thing, it will get the treat, but it doesn't know what it is that the owner has in mind, so it will just commit and try. And based on the things it sees, it will eventually figure out what the task is and do that. So it turns out that the behavior that Perl exhibits is very similar to this. So here's a task that was given to it. So we start at that gray circle down here, and then the only thing we know is that there is a reward somewhere on that circle, but the algorithm doesn't know where it is, right? And what you see here, what are these lines, is the trajectories that the Perl algorithm tries to do. So at first, just randomly tries to commit to a specific goal that it thinks maybe the designer has in mind, and then it tries it a few times until the blue circle depicts the actual reward that's not visible to the Perl algorithm, and then it finally samples the execution of the task that corresponds to it, and then it narrows it down and knows what task it is. And that procedure is also called posterior sampling, since we are using posterior belief to sample what the task is. So it behaves very similarly to what we described as a good strategy for the dog. All right, so that summarizes meta-RL as variational inference. Are there any questions to that? Right. Do you think there are better strategies for the dog or for Perl algorithm for this specific task, other than sampling a specific task and going for it? Can you do something better knowing that there is a reward on the circle, anywhere on the circle?
I think we saw an example where you could go out to the arc and then track it so that you're guaranteed to find it in one trajectory. Yeah, exactly. So posterior sampling might not be the best solution here. And there are other papers that
that do it differently. Yeah, so it's important to keep that in mind. Right, cool. So that summarizes the lecture where we learned a lot about variational inference. Then we presented the framework that allows us to phrase a control or reinforcement learning problem as an inference problem. And that has many other applications that we haven't talked about, but a lot of papers use that, that correspondence. Then we applied variational inference to that problem and saw how we can derive an algorithm by using that. And then using that framework by a simple addition of an additional latent variable that is not visible to us, the task, we arrived at the meta reinforcement learning algorithm that can use off-policy learning and produce state-of-the-art results. All right, so as for next week, we'll try to answer additional questions that come to mind when you think about these problems, such as what should we do if we want the agent to come up with their own tasks? What if we don't want to specify the task and we just want to leave the agent unattended and have them figure out all the useful tasks? How should we think about hierarchies of tasks? And then, can the agent learn continuously over their lifetime? So how can we produce an agent that not only comes up with its own task, it can build its own hierarchies, but also can it do it over the course of its entire life? And next week, we'll talk about on Monday, we'll talk about the first two topics, and on Wednesday, we'll talk about the last one. There's a few additional resources that I encourage you to take a look at. First, there's this really good tutorial written by Sergey Levin on control as inference. If you'd like to learn a little bit more about Perl, there's this quite nicely and simply written bare blog post about it. And then there's also the Berkeley Deep Reinforcement Learning course that also has classes on control as inference. All right, and this is it. Thank you so much. And if there are any other questions, I will stick around. So please just ask.
One quick question. So the kind of additional target of optimizing for the entropy of the policy reminded me of like epsilon, like adding a little bit of probability for your model, like the policy. And I was wondering like how those compare in terms of performance or in terms of theory.
Yeah, that's a really good question. Yeah, so epsilon greedy is kind of like a little heuristic that people came up with to encourage a little bit more exploration. Here we kind of derive a more principled way to do this, in a way that it's not just that we'll try random things from time to time, but we'll try to keep the distribution very wide. So we'll allow the agent to kind of incorporate that into its own objective. It's not that we are altering the algorithm by incorporating that little heuristic, but we tell the agent up front that we want you to be not as committed as you would have been. I think in terms of how they compare, I believe that the state-of-the-art deep RL algorithms use these soft objectives. So things such as soft actor critic, I think, are still one of the best RL algorithms out there, and they use the soft objective that incorporates the entropy. And it's also sometimes what people do is they will still incorporate the epsilon greedy even to the soft objective, right? So that heuristic kind of works regardless where you apply it. So you can do both as well.
Gotcha. Thanks.
Mm-hmm. Right.